Welcome back, everybody. This is our third session in JEE Mains previous year questions for chapter Magnetism and Matter for class 12th. Before this video, we have made two videos in this series, and those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years. So if some of your friends are preparing or you require some extra practice, then you can watch those videos also and can be found in the playlist section of our YouTube channel. If you like these videos, then do press the like button, share it, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. Now, with this, let's start today's video. In the previous one, we covered up to, I think, question 13 or 12th. Yes, 12th, I think. And today we are going to move further. So here is the question: the magnetic line of force inside a bar magnet. So we have to explain that how magnetic field lines propagate inside a bar magnet. So suppose this is our magnet. If this is our magnet, then we know that magnetic field outside moves from, I can say, from North Pole to South Pole, something like this. And inside they move from south to north. Okay, let me draw them by hand. So inside magnetic field moves like this, and outside they form a closed circular loop like this. If this is North Pole and this is South Pole, then outside magnetic field lines move from north to south, and inside they move from south to north. So we have been asked that inside the magnet, so from south pole to the north pole of the magnet, option D will be the right answer here. Let's move to the next one. Iron rod of volume is given, relative permeability if 1000 is given, placed in a solenoid with 10 tons per centimeter. If the current is given, then the magnetic moment of the rod will be. So we have to find out magnetic moment, and we know that in case of magnetic moment, formula for magnetic moment is given by, that is represented by M, and it is magnetic, or we can say, let me, is N I A. This is for normal condition when we don't have a relative permittivity given. In case of when a relative permeability is given, then this formula is modified slightly, that mu r is the relative permittivity minus 1 into NIA. That will be the value of magnetic moment. So it will be 1000 minus 1, that will be 999. Now N will be into N into I into A. Now here we don't have the value of A. Here we don't have the value of A, so we have to substitute A in the form of volume, and we know that volume is given by area into length. So from this, area becomes volume by length. Sorry, that was 999. 1000 minus 1, 999. So 999 into N into I into V by L. Now we have the value of V available with us, but now we don't have the value of N available with us. So what we do? We change this L, remove, we can say move this L2 by N. So this becomes 999 into N by L into I into V. So now this is number of turns per unit length. And we know that there is 10 turns per centimeter, and if there is 10 turn per centimeter, it means it is equal to 1000 turns per meter. This is equal to now small l, where small n, where we have number of turns per unit meter. So it will be 999 into 1000 into 0.5 into volume 10 raised to power minus 3. So these two get cancelled, and this is almost 1000 into 0.5 is equal to 500, or option B will be the right answer here. Let's move to next one. A paramagnetic sample shows net magnetization of 6 ampere per meter when placed in a external magnetic field of zero point 0.4 Tesla. So we have been given value of, we can say, magnetic field B and magnetization or I. So, and temperature is given. When a sample is placed in an external magnetic field of zero point 0.3 Tesla at the temperature 24 Kelvin, then the magnetization will be. So we have to compare here magnetization and temperature, and that can be done with the help of Curie law. From that we know that is equal to I by theta. Or in a more convenient way, or in a more better form, we can write Curie law like this, that intensity of magnetization is proportional to theta, or sorry, magnetic field by temperature theta. And removing the proportionality constant, intensity of magnetization is equal to C is constant, some constant into magnetic field divided by the temperature. And from this we can say constant is equal to I theta by P, or this product of intensity of magnetization into temperature divided by magnetic field is constant. And using this relation we can write that I1 theta 1 divided by B1 is equal to I2 theta 2 divided by B2, and from this value of I2 comes out to be, that will be theta 1 by theta 2 and B2 by B1 into I1. Now theta 1 was 4 Kelvin and theta 2 is 24, so 4 by 24. B2 is 0.3 Tesla and B1 is 0.4 Tesla, and initial intensity of magnetization is 6. So 4 into 6, 6, and we get 3 by 4. 3 by 4 is 0.75 ampere per meter. So option D is the right answer here. Moving to the next one. A perfectly diamagnetic sphere has a small spherical cavity at its center, which is filled with paramagnetic substance. The whole system is placed in a uniform magnetic field B. Then the field inside the paramagnetic substance is. Now, as per statement, the consider this small black dot at the center is the paramagnetic substance which is filled inside the cavity. There is cavity, and inside that cavity we have a paramagnetic substance. And Nearby of that cavity, nearby this substance, there is completely perfectly diamagnetic material. This blue color indicates perfectly diamagnetic material. So as this is the whole blue color is perfectly diamagnetic material, what does it do? It will act as a magnetic shielding. It will act as a magnetic shielding for this paramagnetic material, and as it will provide shielding from the magnetic field, so net magnetic field at point P will be 0, because perfectly diamagnetic material provides magnetic shielding. So if there are some magnetic field lines, suppose there are some magnetic field lines, they will not be able to penetrate. They will not be able to penetrate due to this diamagnetic material. So they will go from the outside, something like this. So it will work as a magnetic shielding, and inside field will be 0. Now let's move to next one. Magnetic material used for making permanent magnets and magnets in the transformer have different property of the following. Which property best matches the type of magnet? And here we have been asked retentivity and coercivity graph. So for the first, let's plot the graph so that we will be able to understand. So that graph looks like something this. The coercivity retentivity graph looks something like this, and we have B here and we have H here. And this term, this is known as coercivity, and this residual magnetic field is known as retentivity. Now we need magnets, we need to make permanent magnets, and permanent magnet has a property that it is very difficult to demagnetize them. If we have a permanent magnet, and it's easy to demagnetize that, to demagnetize it, then it will not be a no longer permanent magnet. So it should be difficult to demagnetize the permanent magnet, and we know that amount of work done needed to demagnetize a magnet is equal to area of uh, this curve, this BH curve. And more the area, more the it will be difficult to demagnetize the magnet. So for a permanent magnet, this area needs to be maximum, and this area will be maximum when retentivity and coercivity both are large. So we can say option C, large retentivity and large coercivity, will be the answer. Now let's move to next one. Here we have again the this BH variation, and it is measured in the ferromagnetic material, retentivity, coercivity, and saturation respectively of the material. So we have to find out what is the retentivity, what is the coercivity, and saturation. So we just discussed in the previous graph that this, in the BH curve, if we have B here and H here, so this is known as coercivity. So coercivity will be here 50. So second term will be 50, and first term, that is retentivity. So this will be retentivity. Retentivity is 1 here. So retentivity 1, coercivity 50, and saturation. Saturation is the maximum value of magnetic field reaching, that is approximately equal to 1.5. So option D will be the right answer here. Now let's move to the next question. A permanent paramagnetic material has 10 raised to power 20 atoms per meter cube. So its number density. Its magnetic susceptibility at temperature 350 is 2.8 into 10 raised to power 4. Its susceptibility at 300 Kelvin will be. So what we will use here? We will use Curie's law that susceptibility is proportional to 1 by the temperature. So we can write Xi1 is proportional to 1 by T and Xi2 susceptibility is proportional to 1 by T2. Using these, Xi1 by Xi2 is equal to T2 by T1, and from this we can say Xi2 is equal to T1 by T2 into Xi1. T1 is equal to 350 and our Xi1 is equal to 2.8 into 10 raised to power minus 4 and T2 is 300. Solving these, we will get 3.226 into 10 raised to power minus 4, 266, sorry. And that resembles with option A. We have also used one other form of this relation, and in some of one of our previous question where I was proportional to I is equal to CB by theta, and we know that these are the here theta is temperature and here T is temperature. These are the same relation but in slightly different form. So let's now move to the next one. A paramagnetic substance in the form of a cube with sides 1 centimeter has a magnetic dipole moment. So we have the volume from side, we have the magnetic dipole moment, and magnetic intensity is applied. So we have to calculate its magnetic susceptibility. So we know that Xi is equal to I by H, where I is the intensity of magnetization, and it is also equal to magnetic moment developed per unit volume. So M by V into H. Value of M is given to us, that is 20 into 10 raised to power minus 6. Volume for 1 centimeter cube, it will be 10 raised to power minus 2 whole cube, so 10 raised to power minus 6, and into H, here it is magnetic intensity, that will be 6 into 10 raised to power 4, so minus 6 get cancelled, and we have 10 by 3 into 10 raised to power minus 4, so it will be 3.3 into 10 raised to power minus 4. Option D will be the answer here. Let's move to next question. At some location on Earth, horizontal component of Earth magnetic field is given. So BH is given to us. At this location, magnetic needle of length is 0.12 meter and pole strength 1.8 ampere meter. It's suspended in the from its midpoint using a thread. It makes angle 45 degree with horizontal in the equilibrium. To keep the needle horizontal, the vertical force that should be applied to one of its end is. So we have to find out the amount of force that's need to be applied, and the diagram for this question will look like something this, that we have needle here. Suppose this is our needle and it is suspended from its midpoint. So it is suspended from its midpoint, and magnetic field is acting. Horizontal component of magnetic field is given to us. Horizontal component of magnetic field is this, and value is 18 into 10 raised to power minus 6. Length of needle is given and its pole strength is given, and this theta is 45 degree. Now, as we can see from this diagram and also from the statement that this is the equilibrium condition. This is equilibrium condition. Equilibrium. So, in equilibrium, we know that potential energy of a dipole should be 0. We have two type of equilibrium of a magnetic dipole versus magnetic field. That one is stable equilibrium and another is unstable equilibrium. We assume that it is in right now in the stable equilibrium, and if it is in stable equilibrium, then its potential energy, we can say potential energy, that is minus m dot b. It should be minimum, with torque that is given by m cross b should be 0. And if we see that we have the value of B and value of dipole moment, that is 1.8 ampere meter. If we calculate torque here, then we will get net value of torque. But for this system to be in equilibrium, the net torque should be 0. And how this will happen? This will happen because there is also a vertical component of magnetic field, and that component should also equal to magnitude with the horizontal component. This is horizontal component of magnetic field, and if we have a vertical component of magnetic field of same magnitude, then the net direction of magnetic field, will be something like this. Now our, we can say, uh, this is yes. Now we have magnetic moment of the needle in this direction and net magnetic field also in this direction. So their theta becomes 0, and if their theta becomes 0, then torque is 0, and we can say potential energy is minimum. So this is the one thing which was not included in the statement, which we have to interpret, because we have been given that needle is in equilibrium. So if it is in equilibrium, then net torque should be 0, and as per given condition, net torque is not 0. So there must be a vertical component of magnetic field which is equal, should be equal, so that their resultant goes at angle 45 degree. So till now we concluded this, that we have a horizontal component and we have a vertical component also. Now it is asked that to keep the needle horizontal, what is the amount of torque applied, needed to be applied. So to keep the needle horizontal, our configuration will something look like this, that if we turn this needle into horizontal condition, so it will be something like this. And now we have two components of field also. One is vertical component of magnetic field and one is horizontal component. Now due to vertical component, there will be a torque acting on this, as between the needle and between the vertical component there is a theta of 90 degree, and due to horizontal component there will be no torque acting on the we can say needle, and this torque is acting about the center, the middle point of the needle. So torque due to magnetic field will be, and that is due to vertical component, it will be bv into magnetic moment, that is 1.8 into sine of 90, sine 90 is 1, and the value of vertical component is 18 into 10 raised to power minus 6 into 1.8, so it will be 18 square into 10 raised to power minus 7. This is the amount of torque acting due to magnetic field on the needle, and we need to balance this torque. If we need to balance this torque, we need to apply an equal and opposite torque. Suppose, first of all, let's find out the direction of this torque. As our we can say torque is m cross b, our needle's magnetic dipole acting in the x direction, and here we have magnetic field in the y direction. So our torque is acting along z axis, positive z axis. So let me draw z axis here. This will be something like our z axis, and we will have torque here, something like this. So we need to balance this torque, and how we can balance it? And we have to balance it by applying force on the one side. So suppose we apply force on this side of the needle. If we apply force F here, then the torque about center point O acting on this rod will be F into this distance, and this distance is half of the length of the rod. So F into half of the length, that is 0.12 by 0.12 by 2, should be equal to, if it needs if we want to balance the torque due to magnetic field, it will be equal to 18 square into 10 raised to power minus 7. And from this, force comes out to be 18 into 18 multiplied 2 into 10 raised to power minus 7 divided by 12 into 10 raised to power minus 2. So it will be 6, 4, 2, 9, or 54 into, I think, 10 raised to power minus 5. And so we made a mistake here. After carefully looking, I realized that it was 1.8 into 10 raised to power 1.8 was pole strength, and we need a magnetic we can say magnetic dipole moment. We need m, and m is pole strength times the length, that is 0.12. So we have additional multiplicative factor here, so that will be 0.12 and 0.12 here. So we will have 0.12 here again, and let me correct this. Let me clear again that in torque we need magnetic dipole moment into magnetic field, and magnetic dipole moment is pole strength times the length of the magnet. So here pole strength is mentioned 1.8, and length of the magnet or the magnetic needle is 0.12. So m is 1.8 into 0.12. So 1.8 into 0.12 into magnetic field will be the torque. So let's now, this 0.12 and 0.12 will get cancelled on the both side, and we will have 18 into 18 into 2 into 10 raised to power minus 7, and this will be equal to 648 into 10 raised to power minus 7, that will be 6.48 into 10 raised to power minus 5, and that is almost option D. So we fumbled a bit, but hopefully we are able to solve this. So the only catch in this question is this vertical component which is not mentioned, and we have to find out ourselves. So with this, we end this video here. Hopefully, again, if you find this videos useful, then press the like button, share it, and subscribe to our channel. And also, if you want to support us, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. And if you want some improvement or any suggestion you have, then you can put them in comment section also. So with this, again, thanks for watching, and we will meet in next video.